Conversely here, remember we have a pin at the base, moment increases to the joint, and then we carry across, and that's consistent. But you see there's some inefficiency in the middle, and then you see in the final one by tuning it. And so when you go out and see pre-engineered buildings, right, like Butler buildings, and you'll see a lot of this kind of shaping of the beam happening because you're trying to make the structure as efficient as possible and eliminate material because the material is costly. Okay. And then down here is just what happens if it's pinned and a load is applied vertically. So you can see that the load is being applied vertically. The structure deflects, right? You get rotation. So at the middle it goes to 0, but you get moment at the joint, right? And that's exactly what that is saying. In the 1M and the 1M match, and that means the sum of the moments at the joint are 0. Questions on that? Okay. And so again, here's a frame. I'm applying a load F. You know, my joint is rigid. I'm rigid at the base, so rigid connected at the base. My deflection will happen as delta D, yeah. And you see it will be consistent, right? And the joint will always be at a 90-degree angle, right? So even under its deflected shape, it's going to maintain that geometry. And flexure happens at the span, and that's the dashed line. You're seeing flexure there. And so the important part is the angle at the joint does not change. Rotation is not allowed, right? That's what moment continuity means. And again, the relationship of ground to beam at a rigid connection would also be 90 degrees, and it would never allow rotation there. Convert that here. Here's a frame with pin connections at the base. My deflection is delta, yeah. It's equal both sides. The joint, I have moment continuity, so I maintain my 90 degrees, but my base is allowed to rotate. So I do not maintain 90 degrees at the base, right? Okay. So that's an important distinction, right? Everybody see that, right? Okay. All right. So then, you know, talking about grillages, right? So effectively, when I look at a grillage like this, so it's a 3x4 grillage of beams, I can cut a section through here. Yeah. And you can see in the metal set of images where the load is applied, and you get 4 points of, you get 4 points of support.
They're nice. It's like they're chill.
Hey, can somebody mute?
I guess it's like cool. Like you open the space and it's like one huge space. Which is different than everything else I've seen.
Who's talking?
The kitchen is amazing.
Hey Sophie, can you mute?
Yeah. Yeah. Can I send you the 2 videos? Check them.
Let's see if I can mute her. All right. Okay, so then you get 3 points of, or 4 points of support. You get at the perimeter, you get the beams in the middle, right? And you can see how you get a sagging moment in between those points of support, and you get a hogging moment where effectively you get an upward bend, right? And this will be true in that kind of condition, yeah? And that's a really important understanding, yeah? Okay. Let's see. So complex beam assemblies. Here's an example of what happens if I install a hinge, right? So I have a beam, I have a fixed connection, I have a roller, and I'm going to insert a hinge. And effectively what that means is I have a beam that spans over the top of the roller in the middle, yeah? And you can see my moment. What happens in that is my moment diagram shifts, and I get a hogging moment coming over the top of the support, right? So there's my support. I get a hogging moment over the top. Here's my max sagging moment. And where I have a hinge, my moment goes to 0. And I can break this down into a system. I end up with one simple supported beam, right? And again, because this is fixed, that hinge is fixed. So there's my fixed point. There's my simple supported beam in the moment. And then again, here's my sagging moment. And then as I start to go over the top of the support, right, I get a hogging moment and then the fade out into a cantilever. All right. And so this is a little trick that we play. And the question always goes, why do people oftentimes on projects move the column inboard of the building perimeter? Well, here's your example why you would do that, particularly if you're tight for space. So simple beam, uniform load applied, I get a moment diagram and I end up with a moment max 1, right? But if I end up moving the supports inboard, right, for effectively the same span, yeah, if I move them inboard and end up with cantilevers both sides, I shift the moment diagram. So in this case, I get a hogging moment over the point of support, and my max moment, M max 2, is actually less than M max 1. And so that's really important to understand that there's a game to be had with your sagging and hogging moments. Okay. And here that we're really talking about that. With a simple beam, we just have a sagging moment. In the cantilever, we have hogging going over the top of the support. You got sagging in the middle. In the case where it's just one cantilever, you get sagging and then hogging, right? And I'm showing here the deflected shapes, right? So you can see what that means to the, you know, if I go back, you can see what that means to the moment diagram, right? And there's what the deflected shape looks like, okay? And these are just some illustrations of, you know, various grillage structures and how that game plays. So, you know, you might ask, you know, what would you be expected to see on a quiz? I might ask you to draw the shear moment deflected shape of beams. And, you know, with the information provided here, you should be able to, you know, out of random scenarios, at least have an opinion about what the moment diagram would look like and what the deflected shape would look like. Yeah. So again, some images of some grillage systems, some images of slab systems. Okay. Any questions on section active structures? The majority of the world out there is section active. So, you know, wood construction is section active. Most concrete structures are section active. You know, bending is the dominant phenomenon, right? And why do you, the question might arise, why is section active more common? Well, it lends itself to prefabrication and manufacturing. So, you know, an I-beam, for example, is a standardized device, and you don't know how exactly it's going to fit into a system. But if it's just going to operate on flexure, then I can make widgets, right? And that's effectively what section active enables. And it enables you to create widget systems that are fairly straightforward, right? I can go down to Home Depot and buy 2x4s or 2x6s, and it's pretty straightforward. I can also go to a still manual and get a modulus out of the still manual, and based upon moments, right, based upon design, I can pick a section that works. And so it is a really kind of straightforward system. It also is a system that is not the most efficient use of materials, right? Obviously, bending means you need to have sectional shape, and oftentimes you need a lot of material because you're not taking advantage of other characteristics associated with structure, and we'll talk about that. Questions? Okay. Next one.
Greg, sorry,
yep.
I have a question.
Yep.
Where else, aside from the book you told us to buy, can we like deepen or look in more detail to this information you are providing?
So I would say, you know, the Heino Engel book is probably as good as it gets.
Okay.
There's another textbook, and I'll have to dig it up. I think it's Form and Structure, but let me look it up. Yeah, but it also is very good.
And could you share with us this presentation? Is it possible?
Yeah. I'll post it on the team site. Yeah.
Okay, great. Thank you.
Yep. No worries. Okay, the next structure is vector active, and vector active, effectively think of it as trusses, right? Planar trusses and 3D trusses. Planar trusses are 2-dimensional, and spatial trusses are 3D or spatial structures. Okay, so in the first, you see a whole series of planar trusses, various shapes, and what is positive about what is positive from a structural point of view with trusses? Why do you think you see trusses applied, in your larger structures?
Like they can save larger cantilevers.
Yeah, larger spans. Yeah,
Yeah, large
cantilevers and
spans.
spans. Yeah, and they're very efficient with their use of material, right? So, section active, right, as I've said, is not the most efficient use of material, right? Because you're putting it into flexure, right? And because you're putting things into flexure, you have to be very, very careful about buckling, right? Because you're putting it in bending, and once things bend, there's a potential for them to buckle, right? So there's some inherent challenges, and that's why, when you're looking at floor joists, for example, they'll be bridging in between the joists so that they remain stable, right? And that's a characteristic of section. With trusses, in lieu of bending, you actually are using triangulation, and you're converting the forces in the system to only axial forces. So every element is either in tension or compression, or there's no force at all. Okay, and so that's a really important piece to say. And when you start doing very large spans, you always convert ultimately from section active to trusses, and you go to trusses to reduce weight in the span, because at some point it becomes non-productive to add more and more mass, right, into a section active system, because it just gets heavier and heavier, and the penalties bigger and bigger. In the case of trusses, you basically have a large filigree, and a filigree is many pieces assembled, and that's how you achieve spans. Yeah. So here you see planar trusses. You see a version of transmitted flat truss structures. You can do curved trusses. Yeah. There's actually a dome truss there. Gridded trusses, which are basically space trusses or space frames, and that's what you're seeing there. So what does that all mean? So I just took this this one element, right? So I applied a load. I've got a 3-element structure. I have a fixed connection, and I have a roller on the other side, right? And if I apply a force to the top, the 2 angled elements go into compression, and the bottom is in tension, right? And so it's a very efficient system because it's triangulated, right? So if that was a column, for example, a vertical element, I would get compression in it, and I'd have to consider buckling, right? And I'd have to design that column not only for the compression force, but I'd have to also design it for buckling. Okay. All right. So what that means, however, is if I were to reduce it into a vector active system, then I want all of the forces to either be registered as tension or compression or no force at all, right? And to avoid bending within the system, I have to apply loads only at the nodes. Yeah. So if I were to apply it at a member, right, a spanning member, I would put bending into an element, and that would be no good. So in the first image at the top, you see a loads applied at the nodes. And then below, you see a series of loads, and I've identified those that are appropriate, right? Where you're applying the load directly on the node, and that is acceptable. And then you see where I'm applying a load somewhere along the span of an element, and I've identified that as no. You'd be surprised how often people apply loads to trusses at the wrong spot, and then you get a failure, right? And it is quite frequent that I go around, and in years past, I've asked students to go out and find trusses where, in Los Angeles, where people have inappropriately applied loads to trusses. And what might be the issue if I apply a load to an element that was never designed for buckling, right? Like if it were to bend and fail, let's just say you applied a load to the top chord of that truss at the top, somewhere mid-span, and you made it buckle, it's in compression. If it failed, the whole roof structure would come down on you. Yeah. So there's some risks, and understanding that important. Okay, so again, a uniform load applied, but again, we're assuming that loads are applied only at the nodes. So if we had purlins, let's say we had a roof, we'd have purlins. Purlins would be coming in and out of page, yeah, and hitting the nodes. And that's how you would capture a uniform load and get it transferred into a truss. You then see, I calculate the moment like any other beam element. I can then take the moment, yeah, divide it by the depth, so the truss depth, and I'll get the chord force, yeah, either compression or tension, yeah. So that's an important piece.
Greg, do we need to learn or deepen through these formulas?
Yes, you'll need to know the relationships. Yep.
Okay.
You can assume if I'm talking about it, it'll be there's a high probability it'll be on the test.
Great.
Okay. And then again, relies on triangulation. Here you can see that a node is identified. There's 5 nodes within this truss. You can see the fixed point, you can see the roller point, and then you can see that if there's 5 nodes, then I know I must have 6 elements, right? And or 6 members. You can see that. And then to calculate the truss forces, at every node, the sum of the forces is 0, right? And so, sum of forces is 0. If it's a 2D truss, the sum of forces in the X and Y will be 0. And if it's 3D, you have to add the Z dimension. And there's a lot of ways you can solve these. You can solve the forces, but you can also draft the resolution. And I don't know if there's anybody that still teaches it this way, but if you draft out each of the nodes, you basically, direction, so geometric direction and force magnitude, if you map that all out, you will actually have a closed loop at each node. And that's what this is saying. So it's kind of an interesting thing, and an important piece, that the sum of the forces is always 0 at every node within the structure. Okay, so vector active, again, here's a truss. You get a 2D planar truss. The next one over is effectively the makings of a 3-chord triangulated truss. It's missing a bottom, but you get the point that I can lead 2 sides on it. And if it had a bottom, what would be the positive in a 3-chord truss or a tri-chord truss? Well, it has cross-sectional dimension, right? So the issue with a planar truss is it wants to twist or warp out of plane when you're trying to place it. But if it's a 3-dimensional truss, i.e. it's 3 chords, it's stable under a lift. And so oftentimes you'll see on very large, long span structures, obviously to get the weight down, they'll do a tri-chord truss or a 4-chord truss, so a box section. And they'll do it because of stability. It won't fall out of plane. It won't twist. Yeah, it won't buckle. And then you can see how you can start to create shapes. Yeah, and so that's the third. Yeah. Okay. And then, this is the making for the discussion of how you make a spatial truss, right? So two planar trusses, you could keep making this additive and eventually you build this up, right? So here's planar, again, going planar. Now I'm inserting the V shape. And if I keep going, I actually have a 3D spatial truss, okay? Because of the uniqueness of geometry, I have a hoop, right? And the hooping action effectively operates as a belt. If I do that, that belt prevents the truss from effectively pressing outward. And I can actually make a truss that spans, and if I stack those up, I can create a dome. So that's a pretty interesting thing. And you often see with dome structures, they get converted to vector active structures, triangulated structures. And, I'll encourage you always to try to think of the fundamentals when you're looking at these structures, and then look at how they start to stack up. Always imagine, and what's important is think about how the structure under load is going to deflect, and then it'll tell you whether it's stable or not, right? If you can really imagine that deflection, you'll have a really great handle on the stability of the structure. Okay. Again, just variations of spatial structures. And again, the key piece is it's always triangulated, right? There's never a rigid joint. All of the joints are effectively pinned and they enable rotation. Okay. And it's the triangulation that locks in the geometry. If I, in lieu of triangulating, let's say if I went to a four-sided shape, would it be vector active?
No, I believe it won't.
That's correct. It wouldn't. If it went to a four-sided shape and you were trying to get it to behave in the manner of a truss, you would
It's like
have
a
to have
frame.
joint. Yeah, it'd end up being a frame. You'd end up with moment at the joint. Yeah. And again, you'd need a lot more material. That's the difference. So, oftentimes you'll hear people say, oh, well, I don't like diagonals. Let's go with a Vierendeel truss. Well, it really isn't a truss, right? A Vierendeel truss is effectively a series of frames and you get bending within the sections. And so it's actually a very heavy approach to make a long span solution, because you actually have section active behavior. Yeah. Okay. And so just ways in which you can imagine, these are planar trusses and you can form shapes. Here's three-dimensional spatial trusses, and you can see how they can make shapes. Any questions on that? Okay, the next one is form active. Form active are effectively cable structures that are dominated by tension. Yeah, so that's form active. So up above, you see a catenary cable with a cast slab. That load is pre-tensioning that cable, so you have stability. Next one over is a cable truss. The next one over is ridge and valley lines. And we'll talk a little bit more about these. You could see effectively a ring in various cable applications there. You can see anticlastic shapes where you get up and down curvature, and then more complex tensegrity narratives in the final two. The other one is tent structures where you have a architectural membrane like PTFE, ETFE, whatever, PVC. What are some of the other fabrics out there that are effectively pulled, and so you can see those structures, right? Also in the form active world are pneumatics. So here's pneumatic structures. Yeah. So structures that are inflated. And then something really cool about form active structures, if you flip the geometry, so if you find the catenary shape and I flip it upside down and I use a rigid material, so I get the correct geometry and make it a rigid material, then I get an arch. Yeah. And these were those Gaudi hanging chain models that are, you know, in the history books that you've read about architecture. That's what he was doing with the hanging chains. And then he was flipping it upside down. And that's how he came up with the geometries for the cathedrals. Yeah. And that was Gaudi doing that. So that's form active. And then sorry, this slide is out of place. Let's see. Yeah, sorry, I would have to back up and get these slides. So yeah, okay, so
are we able to record are we able to record the class, or are we not, or not yet?
Sorry, we're not allowed. Yeah, I got confirmation from the university it's not allowed. I'd have to have a waiver by everybody. And the SCI-Arc is not okay with that. They don't want to carry that liability. What I will do is I will make this presentation available. In other words, the PowerPoint, and you know, and you can always shoot me emails or what have you. And again, we'll hammer this over and over ad nauseum. So, but again, like I said, you know, this is incredibly difficult to teach this stuff. I'm very used to sketching on the chalkboard and being able to register in your eyes, read your eyes, whether you're getting it or not. So if you're stuck or I'm saying something, then just stop me and I'm happy to talk. Okay.
Okay. Thank you.
Yep. All right. So 2 points. Dashed line is effectively horizontal. Assume that both points are on the same plane. It's a horizontal plane to ground. And you get a reaction 1 and a reaction 2. They'll be equal and opposite. Yeah. The cable will be in tension. It finds stability by finding a shape. Yeah. So in this case, there's always going to be some deflection in that cable. Otherwise, it'd be impossible to pre-tension it, right? Like you can pull a cable infinitely, but that cable will have some weight unless it had negligible weight, meaning, you know, it wasn't infected by gravity. That's the only way you'd ever get to that horizontal dashed line. There will always be deflection there, and that deflection tensions the system and you get stability. So, you know, for every 2 points in a given length of cable, just under its own self-weight, it'll find equilibrium given a loading, right? So if it weighs X, that X, and given 2 points of support, it'll find a shape, right? So that's what those next 2 lines are. You know, and obviously the amount of tension in the system will dictate how flat. Yep. The element is in tension, and geometry adjusts to respond to load. That's an important piece. Cables can't take moment. There's no stiffness there. So they're flexible, infinitely flexible. So they're always going to take the shape, right? And that's where the shape conversation comes in. For each load combination, there is a unique shape that corresponds. So if I took this cable and I applied a load at the midpoint, the cable would take a shape more similar to a triangle. And I'll talk about that in a little bit more. Let's see, screen is blocking. Okay. Because of its flexibility, when a cable is strung across a span and loads applied, it can only resist loads by means of internal tensile forces, right? So let's just say it's a horizontal cable. It ultimately has to deflect to resist a vertically applied load. That's what that's saying. And so in order to respond to that load, it immediately configures itself in such a way that it is in axial tension at every point along its length. So in other words, it will deflect into a geometry that you can find equilibrium in the system, right? And again, this is that triangulation, you know, or effectively some of the forces has to be equal, yeah? Okay. So here are 4 diagrams. And the question here is, of the 4 diagrams, based upon what I just said, which one is correct? 3 are incorrect, One is
fourth.
correct. Yeah, it's the fourth, right? I've applied a point and it's deflected to a shape to find equilibrium, right? Like even the third one looks like it could be close, but it would still need to deflect somewhat to accommodate that load at midpoint, right? And it would have some triangulation to do that, right? Meaning you would have to have some vertical component in each of the chord elements from the point of attachment, right? And then the second one, that's not possible, right? It might be possible if it was just under self-weight, but because we applied a point load, that doesn't work. And then the first one is an obvious, no way in heck, because the point load should be at the lowest point, right? Given the loading. Okay. So again, some very particular narratives. The cable will be funicular for that particular combination of loads and support conditions. So cable structures are often called funicular. And you've heard this language before on cable cars. They call them funicular, and it really is about the cable. But in the case of structural engineering, we call them a funicular structure and a funicular shape. And it's basically a catenary shape that's derived from the length of the cable, the points of support, and the applied load. Okay. If we keep the span and loads constant, but change the length of the cable or the height of its supports with relation to one another, the cable will find funicular forms for the change conditions, right? So for every combination, there is a unique geometry associated, right? So if I have a cable and I have 2 points and I have 2 points of support, and I have, 10 different weights that I can apply anywhere along the length. For each combination of position and load, I'll get a different shape, and it'll always be the same. But no two combinations, no two unique combinations ever have the same cable geometry. There will always be a unique geometry. And then the final piece is we cannot force a cable to take on a non-funicular shape, right? It's physics. It will find its natural equilibrium, and that's probably the hardest part about form active structures. They're incredibly efficient. There was an era in the 60s and 70s where you saw a lot of it. Buckminster Fuller was doing it. You've seen Bert Air. They're incredible because they're lightweight and super efficient. But from an architectural point of view, you just can't whip up whatever crazy geometry you want and make it work. It inevitably, what you control is the loading, and the points of support. And at the end of the day, the combination of those two will produce an outcome, right? A final form. And so there's a lot more of an iterative process to ultimately arrive at a design. And that's what this is saying, right? So you could see, given different lengths, you get different shapes, right? With a given load combination, right? So here you see 4 different cable lengths, given 3 imposed loads, right? And here you see, 2 different or 3 different points of support with 3 loads applied, and you can see the outcome in terms of shape. Yeah. Okay, so what's the conclusion from all of this? When designing a tension structure, a form active structure, our task is not to invent a form for the cable, but rather to discover what shapes the cable will take under the assumed conditions of support and loading. Everybody along for the ride? What that means? What that really means is at the end, you're working through an iterative process to ultimately find a final form, and you are playing with the points of support, right? And the loading. Okay. A key piece to tensile structures is they ultimately become incredibly rigid and very stiff. And that enables you to walk on them. So even like an ETFE film, which is the stuff you see on the Eden project that Grimshaw did. I don't know if any of you have been down to Arctic, the high-speed rail station in Anaheim, the football stadium for the Rams, that's ETFE. It's a clear film, and we're talking 250 microns, so incredibly thin, like paper thin in terms of thickness. People can walk on this surface, right? And it has to do with the stability of the system, right? So self-weight, when I say WT, that's weight. Self-weight, pretension's the shape. And so the system under its own self-weight pretensions itself, and it becomes very rigid such that you can walk on it. However, if a disturbing force is applied, stability is lost. For example, wind uplift, and that's what the diagram below. If I were to blow up on the underside of that cable and it lost that tension, the structure becomes unstable, right? And the cable would flap around. And that's an important piece. And you know, you can look up the Tacoma Narrows Bridge, which was a disaster in structural engineering, basically where wind found the forcing function, and effectively the bridge started to rotate and twist, right? And in that process, stability was lost, and effectively the bridge tore itself apart. Yeah. So that case was a case where the harmonics were throwing it out of its rigid state. Here is a cable truss, and you can see a cable truss is composed of a downward curve and an upward curve, and that would be two cables. And then the dashed lines are effectively struts that keep them apart and fix the geometry. And so in this case, you're stable as a planar system, because gravity, you have the downward curve taking on gravity, and you have the uplift curve taking on wind. And that's what this is showing. So the first one is you're seeing what happens if you got wind. The whole thing becomes incredibly unstable, and it would flap much like a sheet in the wind. The next one, you see, you know, what would happen if you applied a load. You'd get that redefinition of the shape. The next one is effectively, you see they applied some mass or showing an indication of mass, and that effectively pretensions the system. Yeah. The next one is, you know, indicating that there's some heft to the cable or the fabric, meaning it weighs something. It may not be precast elements or concrete elements like the one above, but it's enough weight to pretension the system. Going down further, that's a cable truss. And then the final one is, you know, you can tie it down and force the geometry. Okay. The final three images at the base, when you have cables, we're talking very large forces, particularly when you're going long spans and you want them relatively flat. You need to figure out how you resolve the force at the point of support. And in the first one, it's very much like a tent where you get outriggers, and it's effectively a cable anchored to the ground, right? Much like what you see on traditional tents. The next one down is effectively bulkheads, yeah, that are effectively like cantilevered sections. And so you're resolving it with a moment at the base, right? Dulles Airport in Washington, D.C., Saarinen Airport is effectively this, where you get a very large moment at the base, and it's a cantilevered condition. And then the last one is effectively the cables are spanning between perimeter beams, and the perimeter beams are braced at the ends by bulkhead walls that effectively prevent the beams from falling inward, right, in the direction of they're being pulled. And they basically prop or pry the two beams apart and enable the cables to span between. Okay. And the final version is an anticlastic geometry where you get opposing curvatures. So here you see RU, which is a curvature up, and RD, which is a curvature down. So you get double curvature, but they're opposing in geometry, right? So one is operational in the Y, in the Y direction, and one is operational in the X direction. Yeah. And that's an anticlastic shape. And that's most common with tensile structures. And an example of that would be Denver International Airport. That's an anticlastic surface. And that fabric is PTFE, which is Teflon coated fiberglass. And you know, what's Teflon? It's, well, if any of you use Gore dental floss, it's that. Yeah, Gore is Teflon. Okay, and so you can now take these kind of ideas and apply them in scenarios. So Madison Square Garden in New York, or the Forum here in Los Angeles, they are cable rings. So they have an inner hub, and then you have a perimeter ring beam, and effectively you have cables spanning from the hub to the perimeter. Yeah, and you can make a very long span. And in both those cases are arenas. Yeah. So that's what that is. This is a tensegrity dome. So effectively you are building a three-dimensional truss and stacking your way up. And the only thing that is rigid within the system is the vertical compressive struts. Everything else within the system is cable. The last structure in the United States that was a tensegrity dome was the Georgia Dome in Atlanta, Georgia. And if you remember when they were, I believe they were playing the, I believe they were playing a championship football game, but I may be mistaken. It may have been basketball. Anyway, it got hit by a tornado. It survived the tornado, but it definitely bounced quite heavily and was very disturbing for the audience. And I remember watching the YouTube of it recently, and it was quite shocking how much the roof did actually, in fact, bounce under the impact of a tornado. But nonetheless, you know, that's cable and fabric. So imagine a tornado hitting that, and you would think it's going to fall, but it didn't. Yeah. So these structures are incredibly rigid and stable. And, you know, when they went back up there to repair it, they did walk on the fabric to do the repairs. Okay. And then these are anticlastic shapes. And here they're illustrated as cable nets. And what is a cable net? It's nothing more than a grillage of cables. So that you could map this out. You could also do this in fabric, so you wouldn't have to do a cable net. A cable net enables you to use other materials. So I could take a cable net and apply glass to this. Okay. All right, so a pneumatic. So I should ask, any questions? All good? Okay. A pneumatic is nothing more than, you know, like your bicycle tire. You pump in pressure so that P internal, pressure internal, is greater than pressure external, right? So in this case, inside the dome, P internal would be greater than P outside, PO, yeah? And that generates stability. You basically tension up the surface because of the pressure differential. And we do buildings this way. So Carrier Dome, Metro Dome, Detroit had one of these. Effectively, you know, you have to have spinner doors, right? The ones that rotate, and you pump in more air into the building than is leaving the building, and you increase the pressure, and you have a stable roof. So imagine you've effectively inflated the roof. And so you might remember when the Vikings were having their playoff several years ago, folks were supposed to be shoveling snow off, and they had a failure within the roof system and damaged the roof, and they couldn't play their games. So that's an inflated system, or a pneumatic. And then all this is showing is you know, the Gaudi hanging chain. So on the left-hand side, you see a cable net of chains, and you change the boundary condition, you get different shapes, right? So I hang it upside down, I find the tensile shape, the catenary form, then I flip it upside down, and I can develop effectively domed structures. And that's what this is saying. The arch, I have a catenary shape, it's in tension, I flip it, and I get an arch. And note how the reactions at the base change, right? So in a catenary tension scenario, the reaction is up and away. And in the compression side, it's up and inward. So you're basically tying because you get a thrust within an arch. Yeah. So if I were loading the arch, effectively the base of the legs, they want to splay outward, right? And that's why oftentimes you hear about a tied arch. Okay. Sorry, now I got to back up. I had some slides that got lost in the process, so bear with me. Okay. Yeah. All right. So so that terminates or ends the form active discussion. So we've covered 3 typologies. We're an hour and 20 in, so we're not doing too bad. How's everybody doing? Are we completely lost? Are we about ready to roll over and play dead? What's the assessment, guys?
I don't know, Greg, if you could like list these concepts. I mean, like to see them in more detail, and then like make like a profound research in each of them, because it's a bit. I mean, I know it's a general like overview of all of them, but we would like to stop one by one.
Yeah, so I'll start going through some of my own personal projects, and I think it'll help when I do it. I think we have to go through the general, and I get it. I'm mostly worried that, you know, you're just picking up the language and you're grabbing notes, and you definitely need to go back and review the presentation after I go through a few projects. So hopefully, you know, I'll walk you through some projects and talk about these ideas, and hopefully that works out. Yeah, fair.
Because, for example, if I take the presentation and have the book and you recommended on hand, can I like deepen in those concepts in the book? Can I like see?
You can, and I can certainly augment it. There's, like I said, there's another book, and I think it's Form and Structure. I'm in the midst of a move, so I need to unpack my books. So give me a minute and I'll see if I can dig that up. Yeah. And I'll make some proposals. I get it. We're doing this remote, and it's, again, if I had a chalkboard and we could sit there and you could ask questions and I could draw, it would be a radically different piece.
Yeah, because
yeah.
I believe the concepts are quite clear, but if you put me now a formula to know the moment of a beam, I maybe wouldn't solve it right. That's what I mean.
Yep. Okay, got it.
I have kind of like a weird suggestion, and this might be really stupid, but is it possible maybe, like I really, doing the drawings helps me a lot in seeing them, but being able to hear an explanation while you're actually drawing the things out and seeing the process of you drawing it generally helps me. And would it be weird to do like a share screen of you sketching in like Microsoft Paint or in Photoshop so we can see you drawing the things, or would that be weird?
I think, I tried to do something like that. It ends up being fairly painful. And the reason why it ends up being fairly painful is it's one thing to draw, it's another thing to annotate, right? Like I'm operating, in very generic diagrammatic ways, and oftentimes to attach text to it so that people can run away with it and capture it is hard to get both things done simultaneously. Yeah, does that make sense? So yeah, I think it would be great if I could capture giving the lecture and pre-record it and do it on a marker board. but I haven't found the exact, means to make that happen. Yeah.
Yeah, that makes sense. Thank you.
Maybe
Yeah.
with the iPad and an Apple Pencil, you could like write in the iPad or sketching over the presentation. That could work, maybe.
Yeah. Let me keep exploring and see what other options. My Mac is not a sketch narrative, and sadly I'm looking around. I've got every other piece of technology but an iPad. I look at an Apple Watch, an Apple phone, two MacBooks. Yeah. So I think let's keep playing and see what might be possible. Yeah. Okay. All good feedback. Thank you. Okay. The fourth narrative is surface active, right? Different than section active. Next one is surface active, and it is characterized by shear, but shear in plane. So it's about the deformation of the plane, and there are a series of given your feedback, I think I'll produce a set of cheat notes, that probably a 5-page cheat set, that basically what are the main points to remember here. Hopefully that will help. Yeah. Okay. Because I do think that would be helpful. Okay, plate structures, and in this case, they're deep beams, but because they have so much depth, they ultimately distort. So they don't experience phenomenon similar to beams. There actually is distortion of the material in plane, and we'll talk about that a little bit. Next combination are folded plates. So think of origami, right? Like I can impart stiffness to a structure by folding it, right? So if I take a sheet of paper and I hold it up, it effectively flops over, right? If I take it, hold it on one edge and let it cantilever from my hand, if I just hold it, it'll deflect, right? But if I fold it, it'll have stiffness. So let me stop sharing. So if I take a piece of paper, right, look at that, it just flops, right? But if I fold this thing, I've got stiffness. It can actually cantilever, right? And that's all origami is doing, right? And that's what folded plates effectively are doing. I got a few people hanging out. There we go. Okay, so let me go back to share. Okay, so this is folded plates, yeah. And then shell structures are effectively curve systems. So in the case of the first group, those are barrel vaults. In the next, it's domes, right? Then I get saddle shapes, right? So it's like the nuclear cooling tower, nuclear power plant cooling tower. Yeah. And then the final is, effectively curved shapes. So if you saw the cross section of the bottom row, there's curvature, and it's effectively a half curve that if you took a section, it looked like a bird wings. Yeah. So those are those.
Why wouldn't bird wing ones? Why wouldn't those be folded?
They are effectively folded, but the curvature also provides additional stiffness because there's an arching effect. Yeah. But phenomenon very similar, and no doubt it's of the section active variety. So they are of the similar ilk. Yeah. But the curvature imparts certain things to it in addition to the fold. Does that make sense?
Yeah.
Okay. All right. All right. So I want to jump ahead now because I think these slides got lost. Yeah, here we go. Yeah, they did get lost. Okay. All All right. So I want to articulate what I meant when we're talking about deep beam. So on the left, you see what would be more traditional, a section active beam, right? There's some vertical depth and some thickness. And then you also see a slab, right? And it would also be section active. However, when we start to expand the depth of this beam, at some point it transitions into a very deep wall. And that in turn, if you look down on the lower, these are stress plots. So in the first case, you see a layout that effectively you can define the neutral axis and you get this linear relationship of tension and compression. And that's what this sectional drawing here is actually saying. You get this linear relationship. But at some point in depth, that linear relationship starts to mutate. You get curvature there. And that is, in plane deformation. That's the shear acting up. And you can see what that does to my stress plot lines. And if I get it really deep, you can see what happens. And you can see that my stress plot actually really is no longer linear. And that's really where we're talking about surface active when it's deep beams, okay? And so those are stress plots. And then here, these are folded plates, yeah? And you can see how effectively, when it's a planar system, right, there's a tendency for it to want to flex out. And then if you lean against each other, effectively you are creating stability in the system. Okay. And again, just showing the loading applied to a folded plate. Down here on the lower group of slides, so see the third one in. So third one down, third one in. If I take, and I have two planes of material, and I form a fold, right? So I got a fold. It still has stability on the outer edge where I don't get rigidity of the bend, right? Like, and if I took my folded paper analogy, it is very stiff at the fold, but the edge where it's not folded, right? The edge of the paper is very flexible. Well, if I put another bend, right? And that's what this is showing. If I put feet on this thing, it stiffens up the edge and it prevents it from buckling out. And I've got an example project later that I'll show you that phenomenon where I'm stiffening up an edge condition by actually imparting geometry to it. And you might think of back to the section active narrative, right? Like if I can calculate a modulus, right, by folding it, I can actually create stiffness, and that's effectively what you're doing here. It basically forms a beam at the edge. And that's what that is showing. And then
Great.
here's just, yep, go ahead.
Could these surfaces be like normal slabs, like concrete slabs?
Yep,
or
concrete. Yeah, nope, exactly. There's loads of incredibly beautiful, folded origami works, that were done, after World War II, well, and even pre-World War II, in Italy and Southern Europe, and then obviously you had Candela, who's doing some really interesting stuff in South America, which are really, really, really beautiful stuff. So yeah, concrete can be wood. You can do it out of wood. You can even get it out of glass. So glass and composite systems, etc. Okay. And here's just various ways in which you can fold. Yeah, you can do it out of steel plate, for example. Yeah, anything that is monolithic, and as long as you can figure out the jointing, you can even use brittle material. And that's kind of the beauty of it, is you get an enormous amount of capacity out of the folding. And again, just some more variations. And this is a pyramid shape, and it just shows how stability is operational. Yeah. And I think, you know, one of the things I would advise is look at these diagrams and really think about the load imposed and what's happening in the structure is really the best way to think about it. Yeah. Okay. And then here's a barrel vault and the loading of a barrel vault. And you can see how load gets applied and how deformation happens. Yeah. So in the above, you know, the shape gets loaded from the top, right? And it has to deform. And so it pushes out on the sides. Right. And then on the far right, if load applied pushes in and stretches it. And we could also reverse it. We could say, what happens if I had uplift on that? It would obviously drag in the sides. So that's important. And then down here, you know, this is like Lou Kahn's Art Museum in Fort Worth, right? And there's an indication, you know, this is obviously arching between side to side. But it also, because it's spanning from point to point, is actually working as a surface active structure because it's actually a beam spanning between point supports, right? So there is an inherent danger that the initial read is like, ooh, that looks like an arch, but in fact, it isn't an arch. The only place that it really is behaving like the arch is actually at the points of support where it's actually arching from one support to the other, but in between, it's actually acting as a beam, but in this case, it's actually a deep beam because it's shell-like, and therefore it's surface active. Okay, and then here's a dome, you know what's important to note here is you have arching action, but you know as you rotate the arches around the circle. Effectively you establish the circle, and the circle is a really important part to the topic of long span structures, because if I can close the circle, I effectively have a belt. And you know, go back to architectural history, Brunelleschi, you know, he was doing domes and he integrated the chain at the base of the dome to effectively operate as the belt. So as we talked about earlier, an arch ends up having thrust, right? It wants to push itself outward at the base, at the support. And by tying it with a chain, or effectively the circle, you effectively tie the whole thing so it can't thrust outward. Yeah. And that's the beauty. And so in the middle image, right, loads applied, you get deformation, the sides are pushing out, it's deflecting out. But because you have the hoop and the hooping action of the ring, the whole thing is tied. Okay. And you know, this is just showing you know, that's two-way action within a shell surface, right? And that locks in the structure. And and again, there's lots of really beautiful concrete structures that were created. You don't see them a lot because, you know, labor has become very expensive, but, you know, with CNC technology and the like, you're seeing a kind of a new reinvigorated interest in shell structures. And, you know, probably the most prolific character in this space is Patrick Schumacher, that's doing it really, you know, of Zaha's office, who's really pushing CNC technology and computational analysis. So again, just more variations of shells. So, you know, what is the dominant driver? It's always the shear condition, right? And you know, there's always a combination of compression and tension that's happening within these systems, and that's what's driving or producing the shear. Yeah. So in the case of this one, let's just say I look at the point. Can people see my arrow? Can you see my arrow? My pointer?
Yes.
Yeah.
Yes.
Let's see if I can let's see. So if I apply a load here, right, and a terrible color, pin color green, right, I get compression coming down this line. Yeah, so that's compression coming down this line. Because I'm applying that yellow load, it's wanting to fold the thing downward, and effectively I get tension in the surface that's effectively pulling the thing backwards, right? So I've identified damn it, now you see why it would be really painful. So remember, this point load's coming down. It's hard to do this with a mouse, guys, sorry. Compression coming down this line, that's compression. That's compression. And then this piece, you know, wants to pull this way, right? And
Yeah.
effectively that curvature restrains everything from that rotation, right? So that's how that system works. And here's just some additional examples of that. And again, anticlastic shapes, yeah, that are making it functional, that double curvature. And that double curvature actually stiffens the whole thing. So let's just say you lost the curvature. What would happen? You know, the system would buckle, right? And you'd get a failure. And there's been a lot of recorded failures of shell structures where you get a large deflection and the system buckles. And so surface active structures are incredibly efficient because they take the least amount of material and are exploiting geometry to make span. But if you were to lose the shape, the geometry, you lose the stability within the system and you get a failure, right? And so that's the greatest risk. You get buckling within the system buckles, you get failure because you've changed the geometry. And this is just some examples of the kind of spans you can get and the thickness of these spans, yeah? So, and just look at some of these things. So, down here in 1992, the Georgia Dome, you know, spanned 770 feet, and it's, you know, 250 microns, which is, you know, sheet material. A hen's egg, you know, has a span, but look how thin the material is. King County Stadium in Seattle spanned 661 feet in 0.4 feet. So effectively 3 inches, approximately 3 inches of material. Yeah, three and change. So pretty remarkable, you know, the kinds of spans you can achieve in a minimal amount of material. And again, you're exploiting geometry to get there. And there's a lot of geometry that goes into this, and you guys can read up on this. I could make a whole thesis topic of geometry and computation about how you model these surfaces, etc. But I wanted you to have kind of these definitions so you can look that up. Okay, now to examples, and hopefully this helps. Hang on, I think we lost a few characters. Let's see. No. Okay, so this is Gaudi hanging chains, and so you can see the hanging chain models. And if I take a chain and I let it fall into position, that is form finding. And it used to be we would form find shells effectively using chain models to do it. You know, now we have computational tools, and the algorithm to do it is called dynamic relaxation, and it ultimately form find these shapes. And so we can do it by the computer. But it wasn't until very recent that we had the computational power to do it. You know, 20 years ago when I started, we had to at least find the initial shape, and oftentimes refine that shape before we could actually use a computer to resolve that. So, 20 years of computational development, and a world has changed. And so I'm going to show you an example of a project. This is Stuttgart 21. Eigenhoven is the architect. It's advanced. When I started this project, it was probably, 12 years ago, 15 years ago, and we were working with Frei Otto to develop these shapes. And the idea is to find a prefabricated shell unit that would act as a column, but also a skylight, and would enable us to develop an underground station in the square in Stuttgart. And so, again, form finding a tensile structure, right? And why would we form find a tensile structure? Because we don't have buckling, so computation is super easy. We flip it upside down, and now we went from a tensile structure into a compressive structure. So that's the modeling, and this is that structural column, right? So you can see the load applied, and you can see, we broke the perfect geometry of the funnel. And so you have to integrate a strut, which is what that's showing, because we would get some buckling at that location. So take the tensile shape. We have to model it with a hanging chain form. So I'm working from upper left. I'm going to drop to lower left, right? So that's the hanging chain model. Once I find that geometry, I can model that geometry, which is the upper right. And then I can run a stress analysis to ultimately size the shell, which is the thickness of the shell. Okay. And that effectively is a hanging chain model. And in this case, we used nylon, very much like lady nylon pantyhose, but a much more coarser weave. And then all of those are taps that effectively we could scan it and actually scan in those points and get an XYZ coordinate and define that shape. So this is an initial form finding exercise. And then, we worked our way up, and this is a block, hanging wood block model. So, we're giving or assigning weight to the elements. And again, letting that weight fall into shape. So that's what that shape is. And again, just looking at that, and then the translation of, that model into a structural analysis model. And so, yeah, that definitely ages me. So there's an old computer. Yeah, you don't see them like that anymore. And then you can see the actual hanging chain model in the background. And this is the kind of inputs that would get pulled into the computer, and we could run the analysis for that. And I don't know why that's not showing. Anyway, so that was Stuttgart 21, and effectively the form finding of the shapes. I'll talk about another form finding exercise. So in that case, that would have been a shell, a surface active structure, because it would be shell. Yeah, I don't know why those images are not showing. That's frustrating. Anyway, sorry about that. The next one is a art sculpture with Janet Eckelman. She's an artist. She really has leveraged hanging net structures, and really, spent a lot of time in Portugal and Spain, and fell in love with the fishing nets and how they're crafted. And so that's what this is. This is a hanging net sculpture. And if you've flown into San Francisco, Janet Eckelman has sculptures in San Francisco's airport, SFO. But this one, it was actually for Phoenix, Arizona. And so this is that. And this hanging net is composed of effectively the internal funnel and then the base, and the base provides some weight. And then you see a series of pillows that kind of hang off of that internal piece. Sorry, back up. There's the internal funnel, then there's the structural net, and then there's these pillows that hang off of that. So, sorry, in here you can see the cross section. You can see the internal funnel. So this is the internal funnel. This is the structural length, and it's going to support the whole thing. So you can see that there. And then you can see the hanging bits. And each one of those is catenary off of this. Okay. So that's the piece. And this is where, go ahead.
Sorry to interrupt. I think Christy is dropped offline. Can you let her in again?
Yeah, let's see what I can do. Yeah, stop share. Yeah. Yeah, back on. Okay.
Thank you.
Yeah. So this is a trawling net on the left, and effectively on the right, you see is how they actually make these nets, and it's a machine. And effectively, I can pretty much make any shape if I know the distance between knots. So if I know the overall shape and I know the distance between knots and I can map that, I can make this shape. But in the case of Janet's sculpture, I have to form find that shape. And so that's really the problem here, and that's the project, right? So there's that machine and it kicks out netting. So there you go. You can see the distance between knots. And this is what that knotting definition looks like. And at the end of the day, we're going to do a whole lot of sophisticated modeling, but really all I need to do is provide an Excel file that says where the knots exist upon the surface. Yeah. And I'm going to map that against, you know, effectively one strand, one rope of nylon. Every certain distance, I'm going to have a knot, and I'm going to map that. So that's what this is. And so this is a visualization of that Excel file, and you can see effectively a length, and which defines the length between knots, and then and you can see how that weaves into the overall geometry. And as long as I can define the overall geometry, i.e. I can put a mathematical definition to it, then I can make this thing. And so up at the top, you can see that mathematical definition. And on the right, you can see effectively how that all gets tied together. And this is a tool that was built into Revit. It was called the Echelmann Net Layout Tool. And the character I referenced last class, Ian Keogh, he coded this into Revit. And so it was very special and specific to Janet, and it would actually map the locations of knots onto a surface. So again, I have to form find the shape. Once I form find the shape, then I need to be able to mathematically describe the geometry, and then I need to map on the knots. And that's what this tool does. And I want to convert it from a digital representation to a physical reality. And so that's what that step function is. Here is effectively in the red was my starting point, and ultimately I let this thing fall under gravity load into its shape, which is the kind of ghosted look. Yeah, so the shape is fallen into position. And so in the abstract, it was that, but in the reality, this is it. I'm going to let this funnel, this internal funnel, fall into shape. And that's what this represents. And then I'm going to hold that and fix that with this structural netting. And this is what locks the system, and it's a perfect or a pure geometry. And then off of that, I'm going to then establish a whole series of cantilever or catenaries that effectively create this billowing kind of cloud-like art piece. So that's what that looks like. Some more images of what that all looks like. You can see the internal. Down in the lower right, you can see the kind of larger diagrid pattern. That's the structural netting that everything attaches to and basically fixes the geometry. This is the structural analysis of the netting and the loading within the net. And then internally, you can obviously see the blue is the least load, and those are effectively the catenary cloud-like elements that are suspended off of the primary structural net. And obviously the structural net is the larger diagrid pattern, and you can see that it's actually carrying a significant load. So it's on the upper end of threshold, which is in the reds. Okay, and then this is effectively the wind simulation. So under different wind events, the thing will take different shapes. So first one's 30, next one's 60 miles an hour, and the last one's 90 miles an hour. And again, remember, this is Phoenix, Arizona. And then I needed to lock it into place. And so, you know, and what's funny is, you know, we still need drawings to go to a building department. So this is the plan. This is the outer and inner ring. These effectively fix the geometry in space, and then they get suspended from pylons and cables that hold it into place. So the outer tube steel holds the structural net. The inner tube holds the funnel shape. Yeah. And then you could see, you know, effectively the various elevations of this thing. So guys, this is what I took to the building department. And then here is the definitions of the build and how primary hoops are defined. And then this is the knotting that builds this thing and defines the spans. And you can see down here, this is codified, right? This is effectively a zigzag. That red is one of these lines, and then a blue would be another one of these lines. Okay. And then these are the hoops going around, and this IDs where each one of those nylon ropes fits relative to the horizontal bandings. And then you got to have some structural details. Yep, question?
Sorry, Professor. Christy says she's still out of the meeting. Can you check again? Thank you.
Yeah, let's see. Yeah. Okay, back in.
Greg, are we gonna do this in the class? It's very interesting what you're showing.
You know, we won't do it as a computational process, because you can imagine this is really difficult. But I think what's important is that once you start to understand what the principles are, and I'll ask this question: what type of structure do you think this thing is?
Like a cable.
Yeah, it's a form active,
cable,
right? So
yeah.
So if you understand that it's a form active structure, then you can begin to start to establish principles that enable you to work through this kind of stuff, right? And you need that inventory. So, you know, you're conceptualizing an architectural project. You want to start somewhere. You need to have some founding principles that enable you to build upon, right? And so understanding form active ultimately enables this project to emerge, right? And have and enable the conversation with a structural engineer. In that case, myself and my team. Yeah. So these are the structural details. So we won't do anything to this level of detail, but you certainly will be asked to devise strategies and concepts that look similar to this, that you are thinking about how you would actually develop your ideas and then ultimately evolve concepts to get to something, you know, working with an engineer like this project. Okay, does that make sense?
Yes, sure. Thank you.
Okay, so here it is installed. So you can see the 3 masts, right? 1, 2, and 3. Then you can see the 2 rings, and so that's that. And something interesting, it took more time to put up the masts and hang the rings than it did to install the netting and or manufacture the netting. So it took months to get the foundations and get the masts and the cable system all up. It took less than a week for the machine to kick out the netting and for us to install it. The one caveat is that when we initially did the definition and mapped this thing, our math was wrong. We had a negative sign in the equation. Remember that function, that math equation I showed you, if I can define it? We had it oriented the wrong way, and we actually knitted it in the wrong way. So it would have been upside down, meaning gravity would have had to be in the opposite direction. So, you know, even all of the best laid plans, we were wrong. But the fact that it took us a week to effectively remake it was no big deal, and the material could be recycled. So there's the hoops being hung. There is the hoops being hung and the netting, and you can see now the primary lines. So see, these are the horizontals that I talked about. See those coming through, right? You can kind of see the main structural netting. See that line? See that coming through? Yeah. Right. Here's the hoops that tie it all. Interestingly, you know, in a way, this will be in tension, right? Because the net wants to collapse so it has to have thickness, right? So because the whole system is in tension, these hoops need to be in compression. They need to keep from collapsing on themselves. So think of this: if I pulled on the base of this, pull down in tension, right? Effectively, it would want to collapse this ring inward, and to prevent that, I need stiffness there, and it needs to be stiff in compression to avoid that from collapsing, right? And that's what that's doing, and that's why you see a tube shape there, is because it's wanting to collapse. Because it's not a perfect circle, it's got bending in it, and that's why it actually has dimension to it. Yeah, so not only is it in compression, but because it's not a pure geometry, it's got bending, we have to address some bending, right? Okay, so there's this sculpture at night, and you can kind of see the catenaries hanging off, right? Here's a catenary hanging off, right? Oop. Yeah, you can see those things going. Okay, and there's a bigger blow up of this thing, and it makes it even more. Here's the catenary off of that. Again, you can kind of see the primary structural lines coming through. Again, you can see the rings. You can see also my horizontal bands and how each of the nylon ropes was tied to these and basically organizes it. Again, another night shot. And looking down into the internal funnel. Okay, so there you have, so first project I showed you a surface active, a shell structure. Second project I showed you a tensile structure. And this one I'm going to show you a tensile structure, but a hybrid. And in this case, I do not have a membrane material. I have a material that has some rigidity. This was for a competition at CCA, which used to be CCAC, California College of Arts and Crafts, up in San Francisco in their architecture school. And this piece was called the Aortic Arc. And it looked like this. And when the architect came to us, he said, you know, I'm not sure what it's made out of, but, you know, we wanted to have this kind of scaly texture and have this form. And so we worked with them, you know, using the principles of form active structure, but used a cable net to define it. So there's what the conceptual idea looked like. And this is the process by how we got there. This is CATIA finding the geometry. We're going to put a cable net to it. I've got two rings very similar to the Eckelmann project, but I'm going to do another ring down at the base to tension the whole thing so I can pre-tension that surface. So all of the geometry definition, you can see the four rings, the bottom one in yellow, the green, pink, and blue, and working through that geometry. And these were pure geometries, and we modeled this all in CATIA. Right, boundary elements are the rigid elements, and we're going to figure that out. So CATIA geometry, stitch it all together. I got it into Rhino, broke it into parts, right? So primary surfaces. what are my fixed elements? Again, the rings. And then I'm going to break it into a cable net. So I'm going to rule lines onto that surface, and that's what that's doing. And then I'm going to divide those lines. I should correct myself, not ruled lines, but effectively straight line segments, and distribute them equally across these junction points. So here I have a junction line, right? I got a junction line here, and I got a junction line there. And so I basically start and go along one of these hoops, and I say I'm going to subdivide that in equal segments, and I'm going to drop a line. And so then once I know how many lines I'm going to drop, then I got to do the same thing here. I got to divide equally, and same way here, equally, right? And that's what this is representing. So now, and then I come back and I equally divide this, and I establish a cable net. Once I establish a cable net, I get it into Tensile, and this is form finding. I'm going to use dynamic relaxation. I'm going to relax the shape. So again, what's my fixed geometry? That's fixed geometry. I have my intersections. I've now got membrane elements in here, and I've got my anchor points to fix my rings, and I'm going to just to walk you through it, and then I'm going to relax it, right? And this is dynamic relaxation. See how that changed? And I found that shape. I'm going to do it again. See how I found that shape? And again, this is a computational tool that is looking mathematically to find equilibrium. And well, here I go. I'm going to find that shape. So that is form finding using dynamic relaxation. Once I do that, then I get that back into Rhino, and I can map that again. I can clean up that geometry, incorporate that cable net into Robot, which is a 3D finite element software, which is another layer of structural analysis, and I'm going to run it. And what this basically shows is, where I'm getting my axial forces. So you can see the cables are in tension, right? These things are in tension, right? And so that's what's coming out of that. I can also see what my distortion is, right? And you can see this kind of ghosted background, and that step or that distance between, that tells me I've got too much deflection in there, and so I don't have stability within the system. So I got to do another iteration of analysis, right? And you can see how much deflection or deformation I have in the system. You do not want that kind of deformation within the system. And then again, remember I talked on Eckelmann sculpture, the ring, that lower ring effectively pretensions the whole thing, and so it adds weight to the system and pretensions it. But that hoop, because it's not a pure geometry, it actually gets quite flat in some areas, and because it's being pulled, right? Like the upper anchors, these are restraints. This is restrained, this is restrained, and this guy is restrained. And the weight of the lower ring pulls it. The lower ring wants to deform, and that's what you're seeing as these moments. And this is effectively the moment diagram for that ring. So you can see the moment that's happening as it goes around, and that really is bending that's happening within that tube shape. Okay. And again, we have bending on both X and Y because there's geometry here. And that's what this is showing. So again, I'm going to do it again, a revised geometry. This looks like a better mapping. I don't have so much ghosting. Yeah. Run it again as a membrane. And here we are. So I got a membrane. I feel more precise. I can do a higher fidelity analysis, right? So I have membrane elements, and here you can see where I started and where I stopped, right? So I'm clearly pretty tight here, right? That's my initial and my last, and it doesn't pop out. But over here, you can see the deformation's quite large, and that tells me that I still have stability issues. Okay, so I'm going to run it again, refine it. So again, my axial forces and cable in my system. These are my reactions at my supports. So these are my supports. And again, I've defined it by X, Y, and Z. So I know my reactions, and I know the directionality about them. And then I can get into, again, I can run through the process of evaluating the loads, and I can start to see what all of that looks like, because I've managed, and you can still see, still see the cable net coming through there, but it's actually modeled as a membrane. That's what that is. And I'll do that one more time just because you know, there's still some transparency. And then here you can see, you know, so greatly the starting geometry and the final geometry are generally in alignment, right? I have very small deformation or displacements, and so that tells me I'm good. Okay, so that's the modeling process, and form finding is it really is an iterative process. You work through many versions of it to ultimately arrive at a very stiff scenario, and obviously as more and more computational power has come online, it becomes a hell of a lot easier to do this and not have to do physical models. So, you know, that first project I showed you that started with FryAuto, there was still quite a bit of manual interfacing in there. That's 20 years ago. This was done in roughly around 2005, 2006. So, you know, roughly in 10 years, computation power had greatly improved, so that we were purely in a digital space. What do you think this structure might be? Form active, yeah. Now, here's where the trick comes in. We want to do it with this kind of furry section, and remember we have a cable net, so we have a 4-noded net. And so if we take these shapes and we pull a corner and a corner, if we pull those together, I get a three-dimensional shape, and that's what this is. So you can see this is my cable net, but I have no cables. I'm actually using HDPE, which is plastic, and I'm creating these nodes by closing that together. So here, if I kind of theoretically drew, if I drew the theoretical net, my net would look like this. So there's your net. But because I have HDPE and I'm distorting it, and so where I'm going with this is the HDPE, because it has stiffness, out of plane stiffness that holds its form, it actually has surface active. So this structure could be interpreted, depending on what you're looking at, as both surface active and form active. And here's it going together. Some more images of it going together. And again, here's your cable net line. You can see it coming across. Yeah. Okay. And here it's getting installed. You can see how it's furry and how by pulling the corners together, it actually creates shape. You can see the cable net really coming out. Again, here's the form. Again, here's a node coming together. Again, looking from the top, looking down. There's what it was when it was finally installed. And again, this ring much like the Edelman sculpture, you know, tensions the whole thing. Yeah. There you go. You can see it's kind of like a very complex light shade or lampshade. Okay. Okay, so that was you know, form active with some element of surface active. This was Iwamoto Scott out of San Francisco, and they did an installation in Sci-Art Gallery, and it's composed of these petals made out of very thin veneer wood, that so thin that, you know, light effectively comes through there. It's translucent, and so we're going to make effectively a vaulted structure out of these petals. And the vaulted structure, because of the geometry, because of the arching action, you can get a very, very thin surface. If it had bending in it, it wouldn't function. So this is going to be a form active structure with some element of surface active, but really form. And you can see why it's form when I get there. Okay. So we got to form find it. We got to hang it upside down. So it's the hanging chain model. We're going to run the analysis and then kick out the geometry, optimize it. So that's this process. So this is the hanging chain model, right? And so on the left is the structural analysis, and then the overlay of Iwamoto Scott architecture, right? And you can see the improvement. So the initial geometry, trying to build in arching action, you know, max axial compression was 10.7, max axial tension. And again, there's some shell behavior, but principally arching action is 7.7. So we optimized the geometry, we refined the geometry, and you can see the axial compression dropped. It was a 60% reduction. It went to 4.3. And then the axial tension went to 0.2. So in other words, we really did get good effective arching action in there, and we optimized the geometry to do so. And again, you know, what do we not want in there? We don't want bending. So, you know, in the original geometry, the max bending moment was 5.6 pound-inch. But on the right, you can see the revised geometry, the max bending moment was 0.47 pounds-inch. That's a 92% reduction. And again, we don't want bending in a shell, right? So, and or the arch, and that's what we achieved. But where it really matters then is in the deflection. So originally we had 1.4 inches of deflection, and the max deflection after we were done was 0.15 inches. So it's an 89% reduction in deflection. That means we have an incredibly rigid structure, right? All right. Once we had that geometry, then we could work to map on the petals. And so this is a CATIA definition, and we could unfold those petals and map it onto a surface. And that's what that is. And then, you know, we could then take that mapping of those petals and do one more round of analysis. And that's what this is actually doing. And this is looking at the shear force.
Greg?
Right? So, yep, go ahead.
You let Ahmed in because his computer froze, so I guess he got logged out.
Yep, hang on. Stop sharing. Bingo, back in. Okay. So that's the maximum in-plane shear force is. And there's the cardboard mock-up of this thing. It could all be CNC cut. They're building it in the office. Here it's getting installed. You can see how thin this material is. And there it is installed. Yeah. Obviously there's some tolerance issues, but this thing stood for several weeks in the Sci-Art Gallery. And effectively, you know, it was these petals tied together with twisty ties, and, you know, effectively pure vaulting action. And if there would have been any bending moment or any significant bending moment, it would have buckled and collapsed because they're effectively where they tie together. There is no moment continuity there. There is only the twisty tie holding it together. So you can see it installed. Okay, this is going to be the last one, and then I'll let you guys go. We're running a little bit late, but I normally try to do this lecture in 2 classes, but I wanted to pound this thing out. And that's this is really a shell that then gets translated into a diagrid, and so there's some complexity in this thing. This is a Norman Foster project. It's in Washington, D.C. It's Kogod's Courtyard. It's the National Portrait Gallery on 9th and F. The Portrait Gallery is the orange building. The blue is the courtyard. And basically it fulfilled the original design intent to build a botanical garden on the inside courtyard and put a glass and steel canopy over the top to make that enclosure. And it was a competition. And so here's the design. It is effectively 4 supporting columns, and then this glass and steel diagrid structure, glass covered with a perimeter ring beam, which is the heavy gray line around the perimeter. There is a courtyard level, which is this dash line. We had some unique foundation conditions, and so in this case, this is obviously a section active column because it's cantilevered, right? But we're going to resolve the bending with push-pull. So you can see push and pull, and that's how we take it out. So it simplified our footing condition, which was only taking shear and compression, right? So compression is this and shear is this, but no bending. The bending happens by this slab resisting one way and this slab resisting the other way. So it's a force couple. And over here, then this is really a flagpole and a big foundation, big footing with a whole series of piles under it. And then a cantilevered column, and effectively it resists by push-pull. Push and pull. So some nifty ways to resolve bending within a system. Here's the geometry. So working with an architect, you always have to find some agreement. This is the centerline geometry for the diagrid structure. So one thing to think about, is this because it's a diagrid, am I going to have bending in this system, or am I only going to have axial forces? What do you think? Nobody? Because it's not triangulated, you're gonna end up with bending in the diagrid. Yeah. And so therefore I have bending at least in plane within the diagrid. This is all about mapping out the slope, so I can actually put flat panel or flat material on it. I want glass and glass to avoid doubly curved glass, which is incredibly expensive. Bent glass is incredibly expensive. We wanted to flatten the surface, and so that's the CATIA definition. Here you can see where a column comes in. You can see how the structure thickens up because we're concentrating load as the diagrid comes up and over. You can see we have 3 volts. There's 1 volt, there's 2 volts, and there's 3 volts. You can also see, remember when I said I can take a surface and I can bend it up? I'm actually getting stiffness on the perimeter by imparting some geometry. And if I turned it on its side, that geometry looks something like that, which is very similar to like what a C channel would look like, right? So I have some bending stiffness out there because I'm messing with the geometry. And there you can see all of the node definitions, how the segments all come together. And then the definition of the objects. Again, that's digital projects, or CATIA, which was what Frank Gehry's office ran on for a very long time. And then the patterning of the glass onto the surface, and that was all scripted. And then structure, initially we were going to rotate this so it could act as a lamella and provide some shading. At the end of the day, we did flat and it looked like this. So the structure was always normal to the surface. And we did a box section with a round down here. And so that was my structural shape, and sat on top of that. And then this is a track, this is a gutter. And so the glass, which is unitized, sits in there, and I can manage drainage. We learned a lot of lessons off of the British Museum, which was we attach glass directly to steel, and the tolerances between the two, not ideal. And so we had some leakage. And so there's a belt and suspender narrative here. These tracks drain to the lowest point, which is where the column capital exists. So at 8 columns, there's drainage at each of those locations. We end up with a gasket here. So there's 2 lines now. And then I end up with a gasket here and a silicone bead that seals it up. So at the end, I got three lines of defense in my waterproofing detail. Okay, and there's the mock-up of what that looks like. And then to get flat panel glass onto a doubly curved surface, only 3 points of the flat panel material will exist on that surface, and that's a mathematical fact. You can't force 4 points on unless you bend the flat material. And so we had to map that out. And so there's a methodology that we took each half and twisted the corner to give that fish scale narrative, and then a model of the inside. And remember, I talked about Brunelleschi's chain. In this particular case, you know, each of these domes has its own structure, and you can see this line kind of pop through. That's the tying mechanism that ties these columns, because they're very slender, from splaying out. And so it's effectively operating as Brunelleschi's chain, and precludes the columns from splaying out horizontally. And there's what a column capital is. And again, this is that tie that precludes this column from shifting out. And then just because we got to produce some code, we got to satisfy some code jurisdictional requirements, we got to produce drawings. Not very helpful to explain what this project is. Frankly, at the end of the day, the way this was produced, we handed over the digital model. It was manufactured in Poland, shipped to Gundelfingen in Germany, welded together, put together, then taken back apart and shipped in ladders and reassembled in Washington, D.C. That's how it went. So again, another look at that column capital.
Excuse me, sorry. Kate is in
Yep.
a waiting room outside. Is it okay if you let her back in?
Yeah, let me
Thank
see.
you.
Yeah. There we go. Okay. So that's the drawings for that. There's the below. Remember, I said I had a column coming down. Column comes down. I'm going to use this slab push pull to resolve my moment in my column bending. But over here I have room, so I'll do a flagpole and cantilever it and put the piles in push pull. And then here it's being fabricated in Gundelfingen. I actually had the benefit that I followed other people's successes and failures. So just before me, Tom Wiscombe was working for Coop Himmelblau, and he was doing BMW's headquarters. And they were also welding up these structures, and we learned a lot from what he was up to. And this is what a ladder looks like when it's shipped. So it came in containers sequentially, and we installed it. That's what that looks like. There's the scaffolding to set the geometry. You know, with these structures, they fall into shape, right? They fall into a deflected shape. So we had to identify what is the setting geometry and then what the deflected shape was. Obviously, the architect his vision was the deflected shape. And so we had to figure out our starting point, and that's what this is. And once we deprop the shoring, the whole roof will fall into shape. And so there's a ladder being lifted in. Amy Grahek was my right hand. She's right there on the ladder. And every day she would be out there with a computer, taking off geopoints or XYZ points from the survey data. And you can imagine this is a steel structure. So the coefficient of thermal expansion would tell you that as the day changes and it experiences changes in heat, the steel expands. And so she was constantly recalculating the setting out points based upon the temperature. So that was in constant state of flux. Here you can see the structure installed. You can see the cladding. So this is cladding. It was all wrapped in denim. That was the acoustical wrapper. Here you can see the unitized frame that holds the glass. And you can see how these two lines diverge. So you can see that's how we're picking up the geometry. These are effectively called chairs, and these were also our survey points. So each one of those points represented a point that Amy would monitor, but it then allowed us to attach our track, which was the gutter, yeah, and then set on top of that the glass unitized units. And there's a survey station, and here it goes installed. Another survey station you see over here. And again, because we are actually a bending system within these vaults, right? Because it's a diagrid, it's bending, so it's in Vierendeel in plane. We have to have fully welded node points because I cannot allow rotation to happen there. And so what you're seeing is this is a joint that's prepped for a full pen weld. And that means that in plane, this structure will see bending moment within the diagrid. Now, with that being said, it's still a surface active structure. It's just we mapped a diagrid onto it. Yeah. So when looking at this would be a surface active structure with elements of section active taking place. And here you can see the unitized glazing come in. So that's a glazing unit. And then you can see the diagrid coming across. This was a leave out for construction access. This was a mistake. They broke one of these glass panels. There's only one line of symmetry in this thing, and because of how it's laid out, and because glass has an orientation, an outside and an inside, no panel is the same. And so you break one, you got to wait. And this is a consequence. They're waiting for that replacement panel. And this is just how the structure hits and lands at the perimeter. Here you can see that tie coming over, right? And something you might think about. So, the Brunelleschi chain analogy is in play, but also you can also see that, here's my diagrid, but by actually coming across on the diagonal within that diagrid, I've actually stiffened that up. And so in the end, not only is it Brunelleschi's chain, but it actually acts as a stiffening rib because I triangulated it. And you can see that, right? This is clearly a triangle now, right? That's all coming through. So there's a capital, column capital, and there's it hitting, and you can hear my voice almost ready to give out. So that's your sign that I'm almost done. You can see the lighting integration. All of the acoustic wrapper is behind these kind of lines. These are wire rods that are basically the enclosure hiding the steel, and then all the beams were wrapped with denim, which is the acoustic material. And then here's the glazing on top, and you can see how the fish scale happens. And then there's an inside shot of this thing. And the best thing about these things is there's always a party afterwards. So, the more monumental the work, why do we want to focus on large volume architecture is because generally there's always a damn good party afterwards. And they tend to be, you know, your more prominent buildings. So that was the opening. And there it is at night. And that's it. All right. So surface active, also a diagrid. So it's a Vierendeel. So you got some section active narrative. So if you wanted to, if I said, find me a section active structure, you might take a segment of this project and say, here's section active. You might take the whole project and say, this is surface active, and work your way through it. Cool. Questions, comments? I guess the pen kind of worked. I guess the pen kind of worked. Yep.
Thank you for this amazing work. I really loved it. I just have a question regarding the column that you guys made with FryAuto.
Yep.
I've seen it so many times in design of Zaha Hadid architects. What is the story behind that?
Yeah, I mean, I think it's a reoccurring theme. So it really started with FryAuto and Eigenhoven at Stuttgart, and then that project took forever to make real. And you know, Patrick always was really interested in, particularly in his the later years of Zaha's life. He got really interested in form making, and frankly, I think he was very interested in the work that Gunther Banish and folks were doing, and so I think it was just a natural progression that he would take that. No surprise, he's German, and you know, there was always probably some connectivity to that, because a lot of the work that was happening with fabric structures was really happening in that space. And I think if Patrick was here, not to put words in his mouth, but I think, you know, he would reference the works of Gunther Banish and FryAuto, particularly Munich, and as really his starting basis, and the aviary that FryAuto did, etc. So I think, you know, any of the things that I've ever seen Patrick talk about, he kind of starts from those moments of time, and no surprise, there's kind of a lineage, but they weren't intimate in terms of what was going on. I just think it offered inspiration to do it. And again, these systems are very difficult as a starting point. And so you know, no surprise that he probably said, oh, that looks like something I'd really like to deploy. You know, and it's an easier on-ramp to do a precedent study. And I'll advocate in this class that we'll do a lot of precedent studies, because it's easier than trying to imagine something from nothing, right? A blank page is hard to start with, as opposed to having some image in your mind that you've seen somewhere else and then deploying it. Is that fair? Yeah?
Thank you.
Anything more? So, you know, I will show more projects, and then we'll have the first assignment will be to do precedent study and identify 3 structures for each of the categories: form, section, surface, and vector. Yeah. And you'll put a package together, and that'll be your first assignment. But I want to give you a few more projects and talk about how we illustrate that. So next class we'll do that, and then I'll give you that assignment. Yeah. So I'll give you more projects like I just showed. Yeah.
Perfect. Thank you.
Awesome. I think that's it. I'm about ready to lose my voice. I told you that I turn into a pumpkin after 2 hours, and I went a half hour over. So I kind of misrepresented the pumpkin piece, but I do really feel like in the next 2 minutes, my voice will be gone, and pumpkinism will happen here. So any other questions, comments? I guess the pin kind of worked. I mean, it's hard. I'd hate to do a whole lecture crafting everything, but I guess the overlay is okay. Yeah.
Yeah, groups. So we should see the projects you're going to give to us, and then we discuss them in the next class to assign.
Yeah. So so next week I'll pick, you know, I'll pick a form active, a surface active, a section active, and a vector active structure, and I'll diagram them. Yeah. And then I'll give you your assignment and you'll do exactly
Okay.
that I did. But you'll identify 3 of each and do the diagramming that I do. Yeah. So I'll give you an
Okay.
example and then you guys go off and do your own. Yeah.
So from now to the next week, we can just look at these topics and go through
Yeah.
them.
Spend some time with this PowerPoint. I probably won't get it up tonight only because I really am turning into a pumpkin and I literally just moved houses. So I've got chaos here, but I promise I will get it up either tomorrow. Well, I'll get it up tomorrow for sure. I'll get it up first thing in the morning and you can take a look at this. And then if you have questions, let me know. And we'll use Teams as the mechanism to ask those questions. Yeah. And I'll try to check on the team messages, you know, at least once a day, if not twice a day. Okay. Once in the morning and once in the evening. So good. Awesome. I apologize for going long. I promised I would not do it past that, but I wanted to catch up because we did lose some time last week. So I wanted to pound this out, even though it's a little painful. All right. Until next week, guys. Yeah. Take care. Be safe.
Thank you.
Thanks.
Yep. Bye-bye.
Thank you.
Thank you.
Thank
so
you.
much.